Hello students, in this video we will find a formula for the nth derivative or the pth derivative of the logarithmic derivative of an entire function whose order is mu. So let's suppose that f is an entire function of order mu. Then if a1 through an are the zeros, of f, then we have what? Then we have that if I do the derivative p times of the logarithmic derivative of f, this is negative p factorial times the sum, and goes from 1 to infinity, of I'll have an an minus z to the power p plus 1, negative p minus 1, like that. In this case, like this, the pth derivative. Perfect. Okay, excellent. So that's the pth derivative. That's how it depends on p in this formula over here. Perfect. And so how do we prove something like this? Well, the proof is going to follow from Poisson-Jensen. So proof by Poisson-Jensen. We have that what do we have? We have the log of f of z is negative the sum j goes from 1 to n. And let's assume that the modulus of z is on the disk of radius r, right? So for the finite Poisson-Jensen, we get this. And then we'll have what? We're going to have just the log of little r squared minus aj bar z over r and then z minus aj, like that. And then plus the Poisson kernel part, 2 pi, integral from 0 to 2 pi of the real part of r e to the I theta, r e to the I theta, minus what? Minus plus z over r e to the I theta minus z, and then the log of f of r e to the I theta d theta, right? And so modulus of z here is less than r. Excellent. Okay, that's the Poisson-Jensen formula. It's basically just the Poisson formula. I just put in I put a Blashcke factor. This is a Blashcke factor, right? Put the Blashcke factor in there to move z to 0, right? So that's true for any z in this disk over here. Beautiful. And so now, of course, what we're going to do is we're going to find the logarithmic derivative of this thing. So what's the logarithmic derivative? F prime of z over f of z. If we just do the derivative, these ones are going to be very simple to do, right? So we're going to have the sum. J goes from 1 up to n of what? Of just z minus aj to the negative 1 plus the sum j goes from 1 to n of aj bar, and then r squared minus aj z bar to the negative 1, right? Because of that negative sign. And then plus 1 over 2 pi. And then we know what the derivative of the Poisson kernel is, right? The derivative of the Poisson kernel is 2r e to the I theta, and then r e to the I theta minus z to the negative 2 log modulus f of r e to the I theta. Okay? D theta. Now if I do p derivatives of this thing, what's going to happen over here? We do p derivatives of this thing with respect to z. So if I do the pth derivative, we see that the formula is going to be very easily, right? The pth derivative of the logarithmic derivative of f of z. Well, it's going to be negative p factorial, the terms I want, right? J goes from 1 up to n. And I'm going to flip these things, incorporate the negative 1 to the n. So aj minus z to the negative p minus 1. Then plus the sum. J goes from 1 to n. I have aj to the p. And then p factorial, I think. Let's think carefully. Yeah, p factorial. Put the p factorial over there. And then we'll have what? This is going to be the p plus 1. And then rj minus zaj to the negative p minus 1. And then these are p plus 2. So plus 1 over 2 pi, the integral from 0 to 2 r e to the I theta. And then this thing, r e to the I theta minus z to the negative 2 p plus 1, like that. And then what? And then negative 2p plus 1. Just p plus 2. No, that's not quite right. That term is what? That term is going to be negative p minus 2. negative p minus 2, and then the log of f d theta. Okay, good. Excellent. And so now I'd like to show that these terms over here, so let's label these terms something over here. So let's call this term over here, let's call that 1, and let's call this term over here 2. I'd like to show that as n goes to infinity, right? As n goes to infinity, what's happening to r? That means r is going to infinity, right? As r is going to infinity, as n is going to infinity, 1 and 2 go to 0. So I claim 1 and 2 approach 0 as n goes to infinity or r goes to infinity. Okay? So what we'll do is the following. So let's suppose that r is bigger than 2 mod z. Then that's going to force all those aj's. So that says that aj is going to be less than r, like that. Then these terms over here, let's look at these terms in 2, right? The terms in 2 look like aj. So these the 1 terms over here are going to be a sum of things that look like what? Are going to be, I can estimate this in terms of 1 to n. I'm going to estimate that in terms of the number of roots is less than or equal to the number of roots n less than r, okay? Because that's n things, so it's the number of roots here. And so this, of course, is just the number of roots in mod z less than r, right? That's exactly what we have. Good. And then times what? Well, let's estimate these things over here. So if r is less than z over 2, then that says that this factor over here is really like what? That factor over there is really like a r squared over 2, right? So this is really r squared over 2 to the negative p minus 1. So we have a times the maximum of these things. So these things are all less than r. So that's going to be an r to the p plus 1 to the p plus 1. Good. And then so what? And then, good. And what do we need to assume here? We need to assume that p over here has to be bigger than what? P has to be bigger than just the order mu minus 1. Okay? Good. Okay, excellent. So this is going to be an important feature over here. That's one inequality that we're going to need just to make this work, right? And then we have what? And then we have a r over 2. So that's going to be a 2 over r. 2 over r to the what? 2 over r to the negative 2 p plus 1 times a constant c, right? Up to a constant. And then this is less than or equal to what? This is less than or equal to c a to r. And then I'm going to have a 2 to the negative p minus 2. 2 to the negative 2p plus 2. Then we're going to have an r to the negative p minus 1. And now what's the kicker? What we know now is we know that 8 of r by our growth estimates, this is less than or equal to a constant, this is going to be r to what? R to the order, right? So nr is less than r to the mu times this constant 2, I'm going to incorporate that 2 into a constant now, it's just a fixed number over here, times r to the negative p minus 1. But we know that mu minus 1 is less than p, so this is going to what? This is going to 0 as r goes to infinity. Excellent, by this assumption over here. That's good. So that's how we handle the terms in number 1. How do we handle the terms in number 2? The terms in number 2 are handled in an analogous way. What you do is you just say, okay, well, let's count these things by the same estimate over here. What do we really have? The same estimate over here, we have an r, we have a p minus 1. So these terms over here contribute to what? Those terms contribute a r to the p minus 2. So the terms in 2 are estimated by a constant. And then what? And then this, of course, is an analytic function. This p minus 2 is an analytic, this is like w minus z to the p minus 2 is an analytic function, so I can subtract off a constant from this. So this is less than a constant r to the negative p minus 1. Then the integral from 0 to 2 pi of just what? I can quickly bound that. And then I'll have what? I'll replace that with the log of the maximum, mr, the maximum of that function. Right, that's just a constant, which will integrate to 0 because it's an analytic function. And then minus what? Minus the log of f r e to the I theta, like that, d theta, okay? And now what can I say? Well, this thing over here is greater than or equal to 0 by Poisson-Jensen. That's greater than or equal to 0, so I can get rid of it by Jensen. That's by Jensen. And now I can say what? I know how much this thing grows. This is less than or equal to what? It's less than or equal to r to the mu, right? By the same assumption, right? This is less than or equal to r to the mu by our growth assumption. So this thing is less than or equal to what? A constant, then r to the negative p minus 1, r to the mu, right? Now we're done, right? I'm just changing the constant in every step of this over here. And this, of course, tends to 0 as r goes to infinity. Beautiful. So all that's left is what? All that's left is that as, look at this formula over here, all that's left is that as r goes to infinity, what's happening over here? We're going to take this formula and we can replace n with what? With infinity, right? And that gives us our what? That gives us our, a representation, the p-derivative of the logarithmic derivative of an entire function of finite order, right? This is beautiful because now if I have a finite order, I know that this thing looks very similar to what? This thing over here looks very similar to the what? To the logarithmic derivative of the standard part of an entire function. The standard part of an entire function is the Weierstrass infinite product part. That will allow me to say, okay, well now if I take the logarithmic derivative of that, the Hadamard formula will tell me that the rest of that thing has to be a polynomial. And that's exactly what the Hadamard theorem is. And this is the primary tool by which we will get this. So this formula is going to be very useful for us. This formula over here looks crazy, but we need this formula because if we have this formula, this will allow me to prove the Hadamard theorem. Thank you very much.